Hello and welcome to the second lecture of this module, and this module is on common probability models. And in the last class we have covered the normal distribution, some models on this normal distribution, and we have already discussed this common probability distributions in earlier module, in module 3. And from where you have to actually this module, this current module and that module 3 has to be referred to together, because in module 3 we have discussed about the basic properties of all these distributions, and here we are utilizing those properties of those distribution to address some of the real problem in civil engineering. Now, depending on the nature of the problem, depending on the nature of the random variable, we are selecting the which distribution it could follow, and depending, once we are decided that this will follow that particular distribution, and depending on that we are trying to answer several questions that is associated with that problem. But still I should mention here that all this throughout this module you will see that in the question itself we are trying to give that assumption that if this random variable follow that type of distribution. Now, these are all means whatever the example is used and whatever the corresponding distribution is used is from the experience, and that will follow that particular distribution. But there are methodologies how from the data we can determine that yes, this data set will follow that particular distribution. So that goodness of fit, that is called the statistical test from the data, how we can determine that which distribution it is following, that will be taken in the next module, that is module 7. In this module, what we will do, whatever the standard distribution, whatever the standard probability distribution we have discussed earlier, we will be using those distribution to address some real problem of this related to the civil engineering problems. Now, in the last lecture we have covered that normal distribution, and we have also taken some of this some of the problems which can be solved through the normal distribution, and in this lecture also we will take two more continuous distribution, and we will continue to the next lecture as well for another continuous distribution, and after that we will also take that discrete distribution, and that will be we will trying to cover that whatever the standard distribution that we have studied, and their related problems in this module. So, in this lecture we will be covering that probability models using log normal and exponential distribution. These are the two distribution which are also important, and we have seen the many applications are there related to these two distribution. So, these two distribution will be mainly is in our focus for today's lecture. To start with, as you know that we in the last class we have discussed about the several properties, and we have also discussed some problems on this normal distribution, and we will also take some more problems of this normal distribution. As you know that we are giving the that impression that this normal distribution is one of the most common and very widely used distribution. So, whatever the problem we have discussed in the last lecture, we will try to take some more problems here, because the application of normal distribution for the several problems in the civil engineering is manifold, and in this particular lecture we will be taking some problem from the geotechnical engineering problems. And after that, after discussing that problem, even though this lecture is mainly on this log normal and exponential distribution, but to complete that normal distribution, we will take up two more problems on the normal distribution, and after that we will go to the log normal distribution, and we will see that what are the examples of the log normal distribution in civil engineering, and also some specific problem that we can solve from this log normal distribution. Then we will take the exponential distribution. Similarly, what are the different examples that can be modeled through this exponential distribution we will discuss in civil engineering, and we will also take up some numerical problems also, which we will solve in through this exponential distribution. So, we will start with the some two more geotechnical problem in normal distribution. Other problems we discussed in this last class and today's class this geotechnical problem. This problem is mainly related to the settlement, and the first one it is a settlement of a bridge piers. So, a bridge is proposed to build across a stream. It is to be supported on two end piers A and C, and also on a center pier B. The settlement of the piers at A, B and C are expected to be normally distributed based on the observation and analysis of the similar bridges. So, this is what we are just mentioning, that in the problem here we are declaring that this kind of data set is following that normal distribution or whatever the distribution that we will be taking up. So, as it is mentioned here, the based on the observation and analysis of the similar bridges. So, some observation was recorded, data was collected, and from the data we have satisfied that this data set is following normal distribution, and how to satisfy that particular need, that we will take up in this next module through this goodness of fit and different probability papers and all. We will discuss that one later, but for the time being, for this for the discussion for this module, we will be assuming or we will be declaring that this data set is following this particular distribution, and based on that we will solve those problems. So, here also the settlement of the pairs A, B and C are expected to be normally distributed based on the observations and analysis of the similar bridges. The mean and standard deviation of the settlement at the end pair A and center pair B and end pair C are estimated as 0.2, 0.4 and 2, 4 and 2 centimeter and 0.5, 1 and 0.5 centimeter respectively. So, once we are declaring that this is following certain distribution, so that means we also know what are the parameters for those distribution, and for the normal distribution we know it should have two parameters, one is the mean and other one is the standard deviation. So, these mean and standard deviation for all these three support, all these three pairs are shown here. For the end pair A and the end pair C, these are same, the mean is 2 and their standard deviation is 0.5, and for the center one the mean is 4 centimeter and the standard deviation is 1 centimeter. So, then the question is, the settlement are assumed to be independent of each other, means the settlement of one support is independent of the what is happening for the other support. So, we have to determine what is the probability that the settlement in any of these three pairs exceed 6 centimeter. So, what is the probability that any of these thing will exceed 6 centimeter. So, it could be, it is a, so this question is having several events, say that pair A exceeds 6, other two does not, or pair B exceeds 6, other two does not, similarly pair C exceeds 6 centimeter, other two does not, or any of these two, say A B exceeds 6, but not C, B C exceeds 6, not the other one, like that 2 out of 3 we can select, and we can say that those are exceeding, or all 3 can also exceed. So, so this is basically the collection of so many events. So, what is the probability that the settlement in any of these pairs will exceed 6 centimeter? And the second question is what is the maximum settlement of the center pair against which the bridge should be designed such that the probability of exceeding this settlement is 0.0001. So, very less probability is assigned, and what is that settlement that we should consider to design that structure, and what is that particular settlement, so that the exceedance probability of that particular settlement will be 0.0001. So, we will take this first problem to answer. This one is the probability that the maximum settlement is greater than the maximum settlement any of these three one will greater than 6 centimeter, is that probability of x is greater than 6. This x is now a vector. So, any of these things can occur, or the combination of combination of thereof. So, this what we can say that we will just reverse this problem, that 1 minus this 1 is the total probability, 1 minus this none of these pairs is exceeding 6 centimeter. So that is the option that to exclude or to group all the events that will basically taking care of this, whatever this any of this or either of this or a combination of these three will exceed 6 centimeter. So this event, the probability of this event, that is XA less than 6, means settlement at the pair A is less than 6 centimeter, intersection for the B less than 6, intersection with this C less than 6. You know that we have discussed earlier, this means that so all these things is occurring simultaneously. The X that settlement at A does not exceed 6 and settlement B does not exceed 6 and settlement C does not exceed 6 centimeter of the settlement. And if we deduct it from this one, which is the total probability, then what we will get, any of this thing of this support or their combination thereof, whether they are exceeding 6 or not. Now, once we have decided this line, that this is the way we will calculate the probability, rest of the things are, you know, that from the normal distribution is a simple. For this X A, first of all we have to get that reduced variate. Basically we are transforming from the any normal distribution to the standard normal distribution, because we know those values from the probability table, and standard normal probability table is available. So this is that, so 6 is that value minus mean for that support A divided by the standard deviation. So 6 minus 2 by 0.5 is the reduced variate. Similarly, for this support B, 6 minus 4 by 1, and support C, 6 minus 2 by 0.5. So if we do all this, and so this Z1 less than 8, Z2 less than 2, and Z3 less than 8. And you know that for this Z1, this 8 is for the standard normal distribution, this 8 is very high value to easily declare that this probability is equals to 1. And for this 2, we can get it from this table, that this probability will be 0.9773, and this one, this probability Z is equals to minus 8, Z3 minus 8 is again 1. Now, as the assumption was that these settlements are independent to each other, so we can get the joint probability by their multiplication. So that is why we are using 1 multiplied by 0.9773 multiplied by 1. So the probability of any of these or any combination of these three support will exceed 6 centimeter is 0.0227. And the second question was on that the maximum settlement of the center pair for which the exceedance probability is 0.0001. Let this is x. So we have denoting is x, so that the exceedance probability, that means what we look for is the probability of this x b, that is the center one, is greater than 6, is equals to 0.0001. Now, this is the settlement. So what we can write is that we can just convert it to this less than equals to, so the total probability 1 minus this probability, so that will be 0.9999. So now we can obtain its reduced variate. X minus 4 is the mean divided by 1 for the center support, and this is equals to this value. And we know that for this value, from the table we can get that the value of the Z is equals to 3.72. So that's the x minus 4 by 1 is equals to 3.72. So the x is equals to 7.72 centimeter. So the settlement for which the exceedance non-exceedance probability is the non-exceedance probability is 0.9999, and exceedance probability is this one, 0.0001, is equals to 7.72 centimeter. So if we take this one, this settlement into the design, then we can assure that this is with some reasonable probability, reasonably low probability, we can design that center support. Similarly, we can answer similar answer for the other pairs as well for this one. We will take another problem, which is also similar, that is this is basically a structural problem here. So again, the settlement here, what is happening is that there is one thing called the differential settlement. You know, this differential settlement is very important for the structural design, which will basically induce some moments to the structural joints. So here we will see that how to determine, how to see how to control or how to get the probability of the events of the differential settlement. So, the structure rests on three support A, B and C being in between A and B. So, the sequence of the support is the A, then C, then B. Assume that the settlement delta A, delta B and delta C are independent normal variates with mean 3, 3.5 and 4 centimeter, and their coefficient of variation is 20%, 20% and 25%. Now, it is known that A and B have settled 3.5 and 4.5 centimeter respectively. What is the probability that maximum differential settlement between AC and BC will not exceed 1.2 centimeter? So, we know that, so several things has been declared. One is that the settlements are normally distributed, as was also for the last problem. As we have given this, it is the normally distributed, then their parameters are also declared. There is a mean is 3, 3.5 and 4, and their coefficient of variation is also given. That means you know that this standard deviation divided by mu is the coefficient of variation. So, from this information we can get their standard deviation as well. And now, the settlement of two support, basically two end support A and B are given here. So, we have to find out the differential settlement, what should be the maximum, the probability that the maximum differential settlement will not exceed 1.2 centimeter. So, to see this one, first of all we have to find out what is the settlement range that we are talking about for the support C. That we have to find out. Once we find out that what is the range of the settlement at C, then from the information supplied we can get that what is the probability of that particular event. So, for the settlement at A, the standard deviation should be, you know, that CV multiplied by mu, as we have told, that is the standard deviation divided by mu is the coefficient of variation. So, this CV multiplied by mu, so 20% multiplied by its mean is 3 centimeter. So, 0.6 centimeter is the standard deviation for the support A. Similarly, for B, it is that 0.7 centimeter, and for the C, it is 1 centimeter standard deviation. Just we are getting this information from their coefficient of variation. So, now for that delta AC to be that less than 1.2 centimeter. So, what that delta C should be what? So, we know that what is the settlement of this A. Now, the settlement of the A is as explained, the settlement of the A is 3.5 centimeter. Now, if you just see it here, so suppose that this is your support A, then this has already come down to this 3.5 centimeter. Now, we are what is that 1.2 centimeter is the differential settlement. So, it should be either so from this range to this range, this support B can settle, for which the differential settlement will be 1.2. That means it can minimum settlement for this one is that what we are talking about, this minus this 1.2, that is say 2.3. If support B settled 2.3, that means the differential settlement will be 1.2, or else if it settle more and if it goes up to say 4.7, then also we can say that the differential settlement between this A and B will be 1.2. So, this is the minimum settlement possible to maintain that differential settlement 1.2, and this is the maximum possible settlement at B. Similarly, if we see from this support C, and the support C has already settled, that settlement for the support C is 4.5 centimeter. So, it has settled 4.5 centimeter. Now, if I want to see that to maintain this 1.2 differential settlement between B and C also, then this will be 3.3 So this can minimum settlement here should be 3.3, and the maximum settlement that it can come is that 5.7. So now you see, now what we have to find out is that the maximum differential settlement should be limited to this 1.2. So what should be the settlement of this considering both the end support, what should be the range of the possible settlement of B, so that the maximum differential settlement should be within this 1.2 centimeter. So now to see this one, we see that what is the overlap zone for these two possibilities, and the overlap zone is 3.3 to 4.7. So this 3.3 to 4.7. So if the support B settle 3.3 centimeter minimum and maximum is 4.7 centimeter, then we can say the differential settlement should be within 1.2, either between AB or that BC. So we know this range now, and we know the property of this, what is the property of the settlement, probabilistic property of the settlement at B, and we have to find out what is the probability of this support B, settlement at support B will be within 3.3 centimeter to 4.7 centimeter. So this is how the problem reduces to, so which is explained here. For delta AC to be less than 1.2 centimeter, delta C should be between 2.3 centimeter and 4.7 centimeter, and for delta BC to be less than 1.2, delta C should be between 0.3 to 5.7. I did what I have shown here in this diagram is that I just shown that this is that support B and this is support C, but anyway you have seen that this is not the notation that we have used. So this is the support B and this is the support C. So C is between in between A and B. So the settlement for the C is between this 3.3 to 4.7. So so delta C for the delta BC to be less than 1.2, delta C should be between 3.3 and 5.7. So for the maximum differential settlement delta max to be less than 1.2 centimeter, delta C should be between 3.3 centimeter and 4.7 centimeter. So by this one, so the problem now is reduces to the thing that the delta max, this is the differential settlement, to be less than 1.2 centimeter. The probability that delta C, the settlement at C, should be between 3.3 and 4.7. Once we have decided this one, the rest of the problem becomes straightforward. So so this one we can just write the probability of Z or delta C less than equals to 4.7 minus probability of delta C less than equals to 3.3. So after that we can make the reduced variate. 4.7 minus 4 is the mean divided by standard deviation 1, then P Z less than equals to 3.3 minus 4. Let me just check whether these two values are mistakenly given. So C, for the C the standard deviation is 1 and the mean of this C delta C is 4 centimeters. Yes. So this one, the minus mean divided by standard deviation, so which is Z is less than equals to 0.7 minus this Z equals to minus 0.7. Now just to refer that one value, we know that from the symmetry we can change this one as a 1 minus probability of Z less than 0.7, which is the same value. So 7.7580 minus 1 minus 0.7580, which is equals to 0.516. So now what we can take is that log normal distribution, as we are discussing, that we will be taking this log normal distribution here. You know that we have discussed this, their basic properties in the earlier module as well, is that a normal variable x is said to follow a log normal distribution if its probability density function is given by fx with the parameters mu and sigma square 1 by x sigma square root 2 pi exponential minus half log natural of x minus mu divided by sigma whole square, and this and the range of this x is from 0 to infinity. Sorry, this is a mistake, this would be 0 to infinity, minus infinity to plus infinity is the property for this normal distribution, you know. So, this one is the limit from this 0 to infinity. And the cumulative distribution function is that this phi log x minus mu by sigma, where this phi is the standard normal CDF. And you know that if the random variable x is log normally distributed, then if I take their log natural of the data, then that log of that x is normally distributed. So, basically when we are addressing some problem through this log normal distribution, then if we can take if we convert that variable through this transformation, then it essentially reduces to a normal distribution, and once it reduces to the normal distribution, then everything remains same, and we can refer to the again that normal distribution table to find out what are the different answers that we are looking for the different problems. And so, now basically to this transfer, when we are taking that, if we transfer that whatever the data that we have observed, and for that data we can calculate what is mean and what is standard deviation. So, from there there are two possibilities now. One is that one data is available to us, and that we have somehow satisfied that this follows a log normal distribution. So, what we can do, from the original data we can calculate its mean and standard deviation, and through some transformation equation we can calculate what should be the mean for the transferred random variable. Transfer means that through that log natural of that original data set we can calculate that one, or what we can do, the original data set itself, each and every data point we can convert through this log transformation, and we will get a new series, and for the new series we can calculate its mean and standard deviation, solve the problem, get the answer, and that final answer we should again transform back to the original scale, that is by taking the exponential of that particular value to get the answer in the original scale. So, those are the properties. These are also discussed in the earlier module as well. That is, mean of a log normally distributed random variable is given by the mu x equals to exponential of x equals to e power mu plus half sigma square, and the sample mean for the y equals to log x, means after we transform it, is given by y bar equals to half of log natural x bar square. This x bar is the original scale, what is the original data set, that mean, that square, mean of that original data set, that square, divided by CVX. CV is nothing but the coefficient of variation for the data set x, that is the original which is log normally distributed, this x. If we follow this transformation, then the value that we get, that will be the mean for this transformed variable. And similarly, the variance is that sigma x square is equals to the variance of x, which is the mu x square e power sigma square minus 1, and the sample variance for this transformation y equals to log natural of x is given by s x square equals to log natural of 1 plus CV x square. So, CV x is, you know, that this is the coefficient of variation for the data x, where this CV x is the standard deviation of the original data, that is the x divided by its mean. And now, the many real life problems in civil engineering can be modeled through this log normal distribution. The rate of flow in a pipe in a public water distribution system is associated with many losses, and the maximum rate of flow that can be the log normally distributed random variable. The monthly rainfall over a catchment may follow a log normal distribution. The time between the breakdowns of a certain equipment can be a log normally distributed random variable. Basically, these, as I told, that once we have the data set, we can test it whether it is following this that particular distribution or not. And here what you can say is that, you know, that support for this log normal distribution is 0 to infinity. So, the first of all, the example that we are taking care, whether we have to see that whether the support is can go, or that value of that random variable we are talking can go to the negative side or not. If it can go to the negative side, obviously that will never follow the log normal distribution. Now if it is within this, only within this positive side, that is greater than 0, then there is a possibility that it can follow a log normal distribution, because there are other distributions as well with this same support. So we have to test first of all, but whatever is listed here is from the experience, that these are the data set which may follow the log normal distribution. We will take one example on this log normal distribution. A certain data set of timber strength, here the strength of a timber, there are many structures which are constructed with the timber, and we need to know the properties of this strength, and that also are calculated through the probability. So one such problem is taken here on this timber strength. A certain data set of the timber strength is known to have a mean of 39.5 Newton per millimeter square and a coefficient of variation of 0.26. The data set is expected to be log normally distributed. Now determine the modulus of rupture that is exceeded 95% of the time. So this modulus of rupture, the way we define is that in that what is the strength that it should be exceeded, it should be exceeded 95% of the time. That means the probability of one particular event for which the exceedance probability should be 0.95. So that strength should be the modulus of rupture for that particular type of the timber. This is the first question. So we have to find out from this data what is the modulus of rupture, and second one is the what is the probability that the strength of a randomly selected timber of the same type is not less than 20 Newton per millimeter square. So this probability we have to calculate. Now as it is already given that this follow a log normal distribution, so we can use the normal distribution table after we can transform the data through the transformation that y equals to log natural of x, and we have seen in the earlier slide that how to transform this data, because this data what the 39.5 Newton per millimeter square and 0.226, that means that it is the information is on the standard deviation. So these two things has to be first convert to that transform scale, and then we can we can solve this problem, and after that we will transfer back the back transformation of that answer to this original scale to know the answer. So to this one, so first of all we have to find out after the transformation, that is the log natural of this x, what should be its sigma. So this we know that this is that coefficient of variation of the original data set square plus 1 log natural and square root. So it gives you the answer that 0.256 for the sigma, and the mean of that value is mean is that again through this equation, that is mean divided by square root of Cv square plus 1 for this full quantity, its log natural, which is equals to 3.644. So this is now the mean, and this is now the standard deviation for which we have to we can use that normal distribution table to solve this problem first. So now you have seen that the first to obtain the reduced variate corresponding to the non-exceedance probability of 0.05. So that modulus of rupture, the exceedance probability is 0.95, that means the non-exceedance probability is 0.05. So from the standard normal table, so this should be that z less than equals to that specific value should be equals to 0.05. So here we know that from the table, from the standard normal distribution table, that z should be equals to minus 1.645. So this z is now is the y minus that mean divided by this standard deviation, which we just now we got these values at the mean of this reduced variate, of course, that is y, through this transformation y equal to ln x. So through this one, what we will get that y is equals to 3.223. So so the probability of this y greater than 3.223 2 to 3 is equals to 0.95, it will come, but you know that what we are looking for is the strength which is in the original scale. So, so through this transformation we have to back transform this one. So, we have to find out the value of the x for which the y is equals to 3.223. So, the modulus of rupture that is exceeded 95% of the time is the x equals to e power y. So, we will put this value here and we will get that 25.1 Newton per millimeter square. So, the modulus of rupture for this particular timber is your that 25.1 Newton per millimeter square. And the second one, the probability that the strength of a randomly selected timber is not less than 20 Newton per millimeter square is given by that probability that x greater than 20. So, that we can convert that 1 minus probability of x less than 20 here. What we have to do here first in this case is that first we have to find out the transform variable. So, to get this reduced variate in this normal distribution, to use that normal distribution table. So, this one, this 20 we are transforming to this log of that, the log natural of that 20 minus its mean and standard deviation, we will get that z less than or equals to minus 2.532, and after this, after doing this equation, we will get that the probability that is not less than 20 Newton per millimeter square is equals to 0.994. We will take another problem on this log normal distribution. This is on this monthly rainfall over a catchment. So, the problem states in a catchment the monthly rainfall is estimated to be log normally distributed with a mean of 10 centimeter and a standard deviation of 5 centimeter. So, again that instead of providing the full data set, that parameter of the data set is supplied, that is 10 centimeter is the mean and standard deviation is the 5 centimeter, and it is declared it is that log normally distributed. And question is, what is the probability that the rainfall in a certain month is between 5 centimeter and 15 centimeter? What is the probability that rainfall in a certain month is at least 7 centimeter, and what is the 10th quantile of the monthly rainfall? So, first, similar to the previous problem, again first of all we have to transform it from this log normal to the normal distribution case, and for that case we have to transform the mean and transform the standard deviation. And after we transform this one, we also have to find out the corresponding values at this normal distribution scale. What is the value for this 5 centimeter and 15 centimeter, and in between that probability has to be calculated. And similarly for the other two problems also, this is for the 7 centimeter. We have to see that what is exactly is look for this here. We need to know that at least 7 centimeters. So, the greater than 7 centimeter probability we have to deduct from the total probability. And the last one is the 10th quantile. This 10th quantile means that it is that the exceedance probability should be 1 minus 0.1, that means 0.9, and 10th quantile means that it is the it is that non-exceedance probability is 0.01. So, that particular value we have to find out. So, to answer this first one, as I have told that we have to find out that what is the mean at this transform scale, and for which we have to find out what is that CV, that is coefficient of variation, which is standard deviation divided by mean, which is 0.5, and through this transformation equation, this mu of the transform variable is 2.19, and standard deviation of the transform variable is equals to 0.47. Now, using this 2.19 and that 0.47, we have to calculate what is the probability that that x, that rainfall value is between 15 to 5, which we can also write that probability that x less than 15 minus probability of x less than 5. So, this one, I hope that these things, as I have also mentioned in this normal distribution problem, as well as here also we are using, hope that you can see it here, that for the normal distribution what we are, so if this is the distribution 1, So now if this is your say 15 and if this is your say 5, then basically we are interested to this area. Now how we are calculating this one is that probability of this this x less than up to 15. So that's from the 15 to the minus infinity minus what is the from this 5 to this minus infinity to get this area. So this full area minus this area will give you this area. This is what we have discussed earlier also from this area concept of this single random variable. So that is why from this one we are writing that x less than equals to 15 minus x less than equals to 5. Now to again from as we have done for this last problem, we have to first of all find out the reduced variate in this normal distribution scale, that is log natural of 15 minus its mean divided by 0.47, and similarly log natural of 5 minus mean by standard deviation. So these values are giving you that 1.1 and this is minus 1.24, and these two if we just get the values from this table, standard normal distribution table, we will get these values, and the final the probability is equals to 0.757. If we take the second one, the probability that the rainfall in a certain month is at least 7 centimeter, that means we are looking for the answer the x is greater than or equal to 7, which can be again written that 1, that is the total probability, minus x less than or equals to 7. We also have discussed that this equality sign, so far as the random variable is continuous, this equality sign whether included here as well as here doesn't mean anything, because that probability for the continuous random variable, probability of x exactly equal to some specific value is always equals to 0. So that means whether it is included here the greater than equal to and here also it is less than equals to doesn't mean anything, but because that probability x exactly equals to 7 equals to 0. So this one we can again we are just obtain their reduced variate minus 0.52, and from the table we will get the answer that this probability that the rainfall in a certain month is at least 7 centimeter is 0.698. And the 10th quantile of this rainfall value, so let us say that this value is x10. So as I told that this non-exceedance probability should be 0.1. So probability of x less than equals to x10 equals to 0.1. Now we will find out is again the reduced variate, a log natural of that value minus mean by standard deviation equals to this one. Now from the table, from the standard normal table, the value of the reduced variate z corresponding to the non-exceedance probability 0.9 is 1.28. So the value of the z corresponding to the non-exceedance probability of 0.1 equals to minus 1.28 from the symmetry. Some textbook will give you the standard normal distribution for both from the negative side to the positive side, that is from the almost from the minus 3 to plus 3. It will be given. If only the positive side is given, then also using the property of the symmetry we can get these values, that is if it is 0.9 it is 1.28, then for 0.1 it will be minus 1.28, that is what is explained here. So this value should be equals to minus 1.28, where we can say that log natural of x10 is 1.58, so x10 is 4.9 centimeter. So the 10th quantile of the rainfall value is 4.9 centimeter. Now we will take that exponential distribution. A random variable x is said to follow exponential distribution if its probability density function is given by this one, fx of x, this will be capital X, as you know that notation that we are using. The random variable is shown here. So fx of this x with the parameter lambda is equals to lambda e power minus lambda x for the area for the support is greater than or equal to 0, and for the negative side it is 0. So this distribution also we have discussed, we have explained its properties and other things in the earlier module. We will be using these properties now to solve some of these problems in the civil engineering. And we have also seen earlier that the cumulative distribution function of this exponential distribution is again this will be capital X, and this one is 1 minus e power minus lambda x for x greater than or equal to 0, and for elsewhere it is 0. Now, in the civil engineering, the different example that may follow the exponential distribution, that may follow I can use, because obviously any data set that you get, you have to check it first whether it is really following that distribution or not. So, here some of the possible examples are the daily concentration of a pollutant in a stream can be modeled as an exponentially distributed random variable. This is basically the environmental engineering discipline of the civil engineering. It is the daily concentration of the pollutant, which is exponentially the concentration of the pollutant due to its natural decay. It generally we assume it to be decay through an exponential distribution. So, the daily concentration that can be modeled through this exponential distribution. Secondly, the time of operation of a construction equipment until breakdown can follow one exponential distribution. This is that how long that one construction equipment can be utilized before it break down. The time of operation that can follow the exponential distribution. And daily rainfall depth at a station can be can also be an exponentially distributed, but in particularly this daily rainfall depth, when we consider, it may have some significant number of zero values also. So, even though it is exponentially distributed, but there may be a concentrated probability at 0. So, this type of distribution is known as the mixed distribution. The mixed distribution is that it is a mix between this discrete distribution and the continuous distribution, and we will take up a specific problem on this one to discuss this issue. So, so first we will take one problem on this environmental engineering component, where the daily concentration of the pollutant is our concern. In a stream, the daily concentration of a pollutant follows an exponential distribution, which is given by this f(x) equals to lambda e power minus lambda x, and obviously x is greater than or equal to 0, which is the support for this distribution. And the mean daily concentration of the pollutant is 0.0025 milligram per liter. So, why this information is supplied? You know that this mean and this parameter lambda is equals to 1 by x bar, that is the mean of that value of this random variable. So, this we have discussed earlier, how to get this parameter from this data. This lambda is equals to 1 by x bar. So, that is why this mean concentration is given to get this parameter lambda. The question is, consider that the pollution problem is said to occur if the concentration is greater than 0.005 mg per liter. So, if this is the level, if this is the threshold level, to declare that this has followed this has the pollution problem has occurred, then we have to find out what is the probability of the pollution problem on a particular day. So, basically what we have to look that what is the probability that the concentration will exceed this magnitude. Second question, what is the return period of the associated with the pollution concentration of this 0.005 mg per liter. So, this is the return period, means how frequent this problem can occur. So, how frequent this probability can be, so this magnitude can be exceeded, that is known as this return period. So, we will just see how we can calculate the return period from the probability. So, so this answer this first one, as I told that the mean daily concentration is given as 0.0025 milligram per liter. So, this parameter of this lambda is 1 by x bar, that is the mu. 1 by divide this 1 by 0.0025. So, 400 is the parameter lambda, and the probability of the pollution problem on a particular day is probability that x greater than 0.005 is equals to 1 minus probability x is less than equals to this one. We know that from this from the total probability we can calculate, and this pollution problem occurs when this x, this random variable, is exceeding this particular threshold value as declared. So, this we can write that 1 minus this is that cumulative probability f(x), and the cumulative probability is expressed that 1 minus e power minus lambda x, which is essentially coming down to this number that e power minus lambda x, which we can write that e power minus 400 is the lambda parameter multiplied by this x is 0.005. So 0.135 is the probability that on a particular day that pollution problem can occur. And the second one, the second question is that what is the return period associated with the pollution concentration of 0.005 milligram per liter. So this return period can be calculated through that this is the inverse of the probability. So what is the probability that is associated with that particular event? If we just take that inverse of that one, that will give you that what is the return period of that particular event. So as we have got that this probability is 0.135 here. So if we take that in inverse, then we will get that 7.4 days. So on an average, we can approximate that on an average once in a week that pollution problem can occur depending on the data or the information that is supplied for the particular station. So on an average once in a week that pollution problem can occur at that place. Now we will take that another one, that interval time between the successive accident on a highway is an exponentially distributed random variable. So again this is this, so far the accident is concerned, there are two distributions generally we take. One is that if we just count the number of accident over a given time, then that follow one distribution which is a discrete distribution, which is Poisson distribution. We will take up that one later when we are discussing the discrete distribution. But here what we are referring to is that interarrival time between two successive events. So that can be modeled through this exponentially distributed exponential distribution. And the mean interarrival time is 40 days, and one accident has taken place today. If this is the case, then what is the probability that there will be no accident in next 45 days, and what is the probability that another accident will take place within 1 month? Two questions are there, and also first of all we have to calculate what is its parameter. Lambda equals to 1 by 40, which is 0.025, and therefore the interval time between the accident can be expressed as fx x equals to 0.025 e power minus 0.025 x. Obviously x is greater than or equal to 0, and its cumulative distribution is also 1 minus e power minus lambda x, where the lambda is 0.025 x, x is greater than or equal to 0. Now once we get to information, any answer what we are looking for, that first one is that there is no accident within next 45 days. So that means the x is greater than 45 or 45. So 1 minus x less than 45, we can say this is the cumulative distribution. So 1 minus e power minus lambda x, x is 45 here, which we can get that the probability that there will be no accident in next 45 days is 0.325. And the probability that the interarrival time between the accident will not exceed 30 days. No, I think this is written wrong. So the question that we are looking for is that there will be another accident within 1 month. That was the second question here. What is the probability that another accident will take place within 1 month? That means 30 days. Obviously we are considering here 30 days 1 month. So if that is so, please ignore this whatever is written here. So we are looking for the answer, what is the probability that another accident will occur within 1 month. So that means what we are looking for is that x less than equals to 30. So x less than equals to 30 directly we will get from the cumulative distribution, which is 1 minus e power minus 0.025 multiplied by 30. The probability is 0.5276. Well, so in this exponential distribution, sometimes as we are mentioning that it could be a mixed type distribution. So mixed type distribution means at certain point for certain value there could be some probability is concentrated, and one example is taken on this daily rainfall in centimeter over a catchment can be expressed as a mixed probability distribution as follows. So this fx x equals to 0.35 for x equals to 0, and 0.65 multiplied by 0.4 e power minus 0.4 x for x greater than 0. Let me take some time to express this one, how this distribution comes here. For this x equals to 0, that means there is no rainfall on a day, there are 35, the probability is 0.35 that whether there will be rain or not. If there is raining, then that rain is following an exponential distribution with the parameter lambda is 0.4. Now we know that this lambda e power minus lambda x, the integration from 0 to infinity, which is the support of the exponential distribution, will be equal to 1. Now as this is one mixed distribution, so the total probability of this x starting from 0 to 1 is equals to 1. So that means what we are trying to say is that 0 to infinity, fx of x is equals to your dx is equals to your 1. Now at x equals to 0, we know that already that 0.35 probability is concentrated, plus in integration of that exponential distribution, whatever may be the value of this lambda e power minus lambda x dx should be equals to 1. Now we know that this one itself is equals to 1. So if we multiply this one with 0.65, obviously this total amount will become 0.65, and 0.65 plus this one will be equals to 1. So if I just draw that distribution, that is at x equals to 0, there is a probability concentrated here which is equals to 0.35, and then that for this x greater than equal to 0, this is following one exponential distribution, and the cumulative probability also will look like that. It will rise to this 0.355, and then it will gradually asymptotic to the value 1. It will start from here itself. So this is how this mixed distribution is referred here, that is 0.65 multiplied by this lambda e power lambda x, where the lambda is 0.4. What is the probability that the rainfall will exceed 3 cm for a particular day, and what is the 90th quantile rainfall value? So the cumulative distribution is fx equals to 0.35 for x equals to 0. You can refer to this diagram, that at x equals to 0, that fx equals to 0.35, and it is going to the 1. So this is the cumulative distribution, and for the will exceed 3 centimeter, not 30, I think it is, yes, it is 3 centimeter, that is x greater than 3 is equals to 1 minus probability x less than 3, and just we put in this fx and we will get the value 0.1958. And the 90th quantile value is this x 90 equals to 0.9, which is your 0.35 plus 0.65 multiplied by this one, and if we solve this one, we will get that x 90 is equals to 4.68 centimeter. So the rainfall value for which the non-exceedance probability is 0.9, that is the 90th quantile, is 4.68 centimeter in a day. So today's lecture we have seen that some of these examples of the log normal distribution and the exponential distribution. We have discussed one problem on this mixed distribution as well, and we have also taken some more problem on the normal distribution, what was discussed in the last lecture of this module also. And in the next lecture we will be taking some more continuous distribution and their that application in different problems in civil engineering. Thank you.